Okay guys, so now this might be my favorite example for derivative proofs. This is f of x equals e to the x. Okay, um, we're going to go ahead and jump right into this. Just remember you should watch the lesson on the definition of derivative explained, or the difference quotient explained. That way it will make more sense as to why we're using this formula. So this example, we want to find f prime of 1, meaning the derivative at x equals 1. How do we do that using a derivative proof? Well, the first thing to know is you need to write out the difference quotient, or the definition of the derivative. F prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. Once we've read out the definition, we then want to figure out both f of x and f of x plus h. They gave us f of x equal to e to the x. F of x plus h is just plugging in x plus h in for x. So every time there's an x, we're plugging in x plus h. So f of x plus h is equal to e to the x plus h. Now we're going to be plugging that stuff into the formula. So for f of x plus h, we would substitute with e to the x plus h, and we replace f of x with e to the x. So we have f prime of x equals the limit as h approaches 0 of e to the x plus h minus e to the x over h. The real question is, like in the previous examples we saw, how are we going to cancel the h on the top and bottom? This I will explain to you. So, step 4 we said is manipulating algebraically, and basically what that means is we want to get to a point where an h on the top will cancel an h on the bottom. The first thing we're going to do is notice that you can rewrite e to the x plus h as e to the x times e to the h. Why? Because if you multiply like bases, you add the exponents. So that will become e to the x plus h. We're doing the reverse though, so we're going to split it up into e to the x times e to the h. So now we can pull out an e to the x because both terms have an e to the x. When we pull out an e to the x, we're left with e to the h minus 1. Here's where things get interesting. I don't know if you knew this or not, but e actually comes from a limit. Okay, e is the limit as h approaches 0 of 1 plus h to the 1 over h. Okay, it's pretty crazy. If you were going to your calculator and plug in really, really small numbers for h, say 0.00001, you're going to get something close to e, which is 2.718. In fact, I will do one demonstration for you. Okay, I'm using Desmos, the online version, which is an excellent graphing calculator. And I'm going to type in 1 plus, now for h, I'm going to plug in something really small like maybe 4 zeros and a 1, okay? And then I'm going to raise that to the power of 1 divided by 0.00001. And notice what number I get back. Okay, it looks a lot like e, 2.718. And so e is just the limit as h approaches 0 of 1 plus h to the 1 over h. And in fact, that's what e is. That's the definition. And so we're going to use this definition, this limit definition, to replace e with this limit. And so notice this e right here, this e to the h is going to be replaced with this in the next step. So that e to the h, this e becomes 1 plus h to the 1 over h. We can do that because we are already figuring out the limit as h approaches 0. Since we're already figuring out the limit as h approaches 0 and e is equal to that limit, this e right here will replace with 1 plus h to the 1 over h, and it becomes that. Now notice we still have an h exponent out there. It's this h exponent right here. The only thing that changed was this e. But if you raise something to the 1 over h power, and then you raise that to the h power, 1 over h times h is 1, so you're actually left with just 1 plus h right here. And then guess what? Now the 1's cancel, so now you're left with e to the x times h, which is beautiful, because now we can cancel the h's, which is our next step. Step 5, cancel the h on the top and bottom, so those h's cancel. So now we just have f prime of x is equal to the limit as h approaches 0 of e to the x. It's a little bit different than the proofs we did before. There's no h to plug in, but that's okay, right? I mean, if there's no h to plug in, then it really doesn't matter, if h approaches at 0 in terms of plugging in 0 for h, there's nothing there, okay? So it's kind of becomes irrelevant because it's always going to be e to the x. Okay? So guess what? When you plug in 0 for h, there is no h to plug in, so the derivative of f prime of x equals e to the x itself. Now, why I love this example so much is because look at the original function. The original function, f of x equals e to the x. But what's our derivative function? It's the same thing, f prime of x equals e to the x. This is the only function that I know of where its derivative is the same as its original equation. And again, what does this equation mean? It means that for any given x value, say we wanted to figure out the derivative at x equals 3, we could plug in 3 for x, and the derivative would be e cubed. But for this particular example, we want to know what f prime of 1 is. So for our final step, after we figure this formula out, we're going to plug in 1 for x. So f prime of 1 is just when you plug in 1 into the derivative formula, and the answer is e. So f prime of 1 equals e. Now we're going to take a look at this graph, and we're going to see exactly why this is. So in other words, the slope of the tangent line at 1 should be about 2.718, which is the same as its function value. Okay, if you plug in 1 for e, you also get 2.718. Again, that's the only function I know that does that. So here's our function, and basically what we're going to do, we got h, being, I didn't mean to do that. We got h being a 1 here. We're going to draw it closer and closer to e. The y value to e, and x is going to get, the x values are going to get closer and closer to each other. H is going to become 0. Now notice the y value is 2.718. When h becomes 0, notice what the slope of the tangent line becomes, also 2.718. Again, it's the only function I'm aware of where the slope of the tangent line is equal to its x value, and this is going to be true for every single x value. If we were going to figure out, for example, let's just plug in 2 real quick. This shouldn't take too long. Notice that the y value at 2 is 7.38906, but so is the slope of this line. Slope of this tangent line will always be the same as its y value. So there you have it, folks. There is the definition of the derivative, using that to prove the derivative of e to the x at a certain x value. In fact, for all x values. The last thing I want you to remember before we complete this series on derivative proofs and the derivative definition is all of these things mean the same thing. Instantaneous rate of change is this formula that we learned to begin with. The limit as x2 approaches x1 of f of x2 minus f of x1 over x2 minus x1, which we said comes from change in y over change in x. Same thing you learned when you learned the slope of the line in Algebra 1. That's all this is the same as the slope of the tangent line. It's the same as the instantaneous rate of change. The word derivative means the same thing as those two things, and this is the ultimate formula. F prime of x equals limit as h approaches 0 of f of x plus h minus f of x over h. We can use this to prove all future rules that we will learn, which will make finding derivatives a lot easier. So again, if you have any other questions about derivative proofs, let me know.